purifications.
Thanks, Ignacio. Thanks to Eric. It's great to be here. So I'm going to talk about work I've been doing in collaboration with Brian Swingle, two grad students at Princeton, Trip, and Matt Halbosch, Phuc Nguyen, and then also the group working with Frank Pullman at Munich. So the approach to entanglement I'm going to be talking about in this talk is entanglement not so much as a way to characterize many body theories, but as one of the barriers to simulating them, or at least simulating them on a classical computer. So the concrete scenario here I'll be talking about is many body systems in one dimension. So a clear example of how entanglement is a barrier to simulating one-dimensional states is given by the matrix product state ansatz. So a brief review of matrix product states. You should think of them as a variational ansatz for one-dimensional many-body systems. The variational parameters are a set of matrices or tensors B. And you get a many-body wave function by taking one tensor per spin in your system and contracting the indices together in this manner here. So going forward, I won't actually write out the indices, we just write a picture. So each node of these lines here represents a tensor, and if legs are contracted together, there's the Penrose notation, that means the indices are summed over. You're left with a series of dangling indices. Those are the indices representing the spins up or down. And each of these tensors B is the tensor of the matrix product state, and an important parameter we're going to be using throughout is this chi, the so-called bond dimension. It's just the size of the tensors. So if you have tensors with small chi, they're easier to work with, but you have a smaller variational space, and as you increase the rank of the tensors, you have a larger variational space, but the numerical algorithms tend to increase in complexity as chi cubed. Okay, so the basic question then is, how big do the tensors need to be if you're going to represent a given many-body state? This is where entanglement comes in. So let's consider our 1D spin chain here. We partition it into a left and right, and then we compute the entanglement entropy S associated with a left. And it's very simple to show that to represent this state, the size of the tensors chi is going to be bounded from below by the log of the entanglement on the left. So this is just a trivial lower bound on the size of the tensors. Morally speaking, working by Hastings and others has shown in 1D that in some sense this is an equality, or at least that if there is an area law for your ground state, it can be represented efficiently with a matrix product state. So this, yeah. The bond dimension has to be bigger than the entanglement. So the more entanglement, the larger the size of the tensors. Yeah, so it's only a special set of states where this would actually be an equality. Usually it's a lower bound. Okay, so that was the setting of working with pure states. So entanglement entropy, the von Neumann entropy, lower bounds the size of the tensors for representing pure states. It's natural to then ask the question, what if we instead want to represent mixed states? So states at finite temperature, or doing non-equilibrium dynamics, finite entropy density. What then bounds the size of the tensors when simulating mixed states? So in simulating mixed states, there's actually a couple different approaches. Let me just review three of them. The first is due to Frank Verstraete, Ignacio, and others, which is you can work with a density matrix, and then we can generalize the matrix product state ansatz to the so-called matrix product operator ansatz. So basically what happens is you still have a set of tensors you're contracting together, but now because we have an operator with both a bra and a ket, you just have twice as many dangling legs. So you can use this as your variational ansatz. Another somewhat different approach is due to Miles Studenmeyer and Steve White, called minimally entangled typical thermal states. The idea here is if we have a density matrix we want to represent, let's say we're in equilibrium, it just takes this form here. So what you do is you split the computation into two parts. These you let be classical spin configurations, like up, down, and you do classical Monte Carlo sampling over these unentangled states here, and then for each unentangled state there, you do the time evolution algorithm on the product state using sort of standard 1D matrix product state methods. But the type of approach I'm going to talk about in this talk is so-called purifications. So let me review what purifications are. The idea of a purification is, suppose you're given a mixed state on subsystem A, so that's row A. It's always possible in quantum mechanics to represent the entropy of the mixed state as instead entanglement with some ancilla. So throughout this talk, the ancilla is going to have a primed index. So we so-called extend the mixed state by finding a pure state on the larger system of A tensor A prime, such that if you were to trace out A prime, you get the mixed state of interest. Now, given a particular mixed state, there's actually many different purifications you can find which are going to be valid, and that's because if you act with an arbitrary unitary operation on A prime, since you're tracing it out, that doesn't actually affect the mixed state on rho. So you can always find a purification, but it's not a unique thing. So a particularly convenient one is the so-called Thermofield double purification, which many of you probably worked with. The idea here is, in some sense, you can always let the purification be the square root of the density matrix. So given an equilibrium density matrix on the left there, we just sort of flip over the bra and turn it into a ket and view it as a state in the ancilla, and then just have the Boltzmann weights. So it's easy to show, because this is diagonal here, that if we trace out over A prime, we get the density matrix on the left. So the matrix product state of purifications is, this purification here is a pure quantum state. It just has twice as big a Hilbert space. And the ancilla Hilbert space in this case is an identical copy of the one we started with. So it means that your pure state, your purification, can again take this form. It's just that now your spin is doubled with the physical and the ancilla one. So one of the advantages of using purifications over density operators, I mean, the ansatz in the end looks the same, but it guarantees certain nice properties like positivity. In general, if you took a general MPO and we're trying to approximate a mixed state, you're not actually guaranteed basic properties like that it's going to be trace preserving or that it's going to be a positive operator. Working with purifications, any matrix product state for purification, just because of the way you evaluate operators, gives a valid mixed state. Another possible advantage of it is that, at least if you're working at finite temperature states, you can see it takes the same form of the equilibrium density matrix, but at half the temperature. And we expect that at lower temperature, at twice the temperature, and we expect that at higher temperature, there's going to be less entanglement, so it's going to be easier to represent. So the usual way that people would obtain the Thermofield double purification is as follows. You imagine starting at infinite temperature. So I'll write that as the state ket, the state on the right, 1 there. And if you view the state as an operator, it's just the identity operator. You're just gluing every state with every other state with equal magnitude. And then you can obtain the finite temperature Thermofield double state by acting with imaginary time evolution just on the physical side, just on the physical degrees of freedom. So drawing that in pictures there, if you start out at infinite temperature, the matrix product state is very trivial. It actually has bond dimension 1, because it just acts as the identity from the ancilla degree of freedom to the physical degree of freedom. So that's trivial to represent. And then starting with that, you slowly start cooling it down by acting with a trotterized version of the imaginary time evolution on the physical degrees of freedom here. So what I'm representing here is taking the general imaginary time evolution, trotterizing it into 2-site gates, and you sequentially start applying the gates to the MPS ansatz, and then at each step compress it back to matrix product state form. So this is a standard. There's many ways to do this, but standard one is time evolving block decimation due to Vidal. So in this approach, what is going to be the way entanglement manifests a barrier to the difficulty of doing this? Okay, so remember, purification takes this general form that we started with 2 subsystems, A and B, with a mixed state, and we can think of turning it now and viewing it as a pure state on 4 systems, where the A prime and B prime are the ancilla here. So this pure state on the left is being represented as a matrix product state, where these degrees of freedom are the physical ones on the left and right, and the top are the ancilla degrees of freedom on the left and right. Now, what bounds the difficulty of the matrix product state is the entanglement between the entire left and the entire right. And it's not just the entanglement between A and B, it's the entanglement of A plus A prime and B plus B prime. Okay, so let's call that entanglement SAA prime. So we get a trivial lower bound on the size of the tensors, which is that they're going to be exponentially large in the entanglement of the purification between the left and the right. And at least in equilibrium, actually, you can show that not so much that this is equality, but for the Thermofield double state, you end up with something which gives polynomial efficiency in the temperature. Okay, so this tells us that to get efficient simulations, we'd like to have purifications which have low entanglement in the sense of between the left and right. So the natural question you'd then ask is, we said there's actually many possible purifications, not just the Thermofield double. Can we use that ambiguity to lower the amount of entanglement and therefore make the simulations more efficient? So to see there might be something to gain here, let's actually consider the limit at low temperature. So let's go all the way to 0 temperature, where the Thermofield double state would just give 2 copies of the ground state, 0 and 0 prime. So what's the entanglement of the purification in this limit? Well, if I draw a picture, the physical ancilla aren't related at all. You just have 2 copies of the same state. So the entropy of the Thermofield double states can be twice the ground state entropy of just a single copy. So could we do better than that? We certainly could. A much better purification, or at least a lower entanglement purification to use at 0 temperature, is to let the ancilla just be all up, so just a completely unentangled state, whereas the physical one is the ground state. So the entanglement of this purification is now just the entanglement of the ground state. So you cut the entanglement in half, and if naively we say that bond dimension goes exponentially, or the size of the tensors goes exponentially in the entanglement, cutting the entanglement in half would give a square root improvement in the efficiency, which could be a big advantage. Okay, so this is a trivial limit where it's possible to do better, but we could ask, how do we interpolate or minimize the amount of entanglement at intermediate temperatures? And the idea is I want to think about this as starting from here and going to here was basically disentangling the ancilla. So this problem has actually been considered, I think it was first considered in 2002 in this paper, and given the name of entanglement of purification. So the problem here is, given a mixed state, there's many purifications. There's purifications here. Let me optimize over all possible purifications so as to minimize the entanglement between the left and the right. And you call the value of that minima the so-called entanglement of purification between A and B. So it's an entanglement measure on multipartite states. A couple facts about it. So it's lower bounded by mutual information and upper bounded by the entropy in either the left or right region. And in general, it's sensitive to both classical correlations and quantum correlations. So we know trivially at least that the optimal MPS now is going to satisfy this bound, that the bond dimension of the MPS is going to be exponential in the entanglement of purification. Entanglement of purification. Oh, what do you mean by entanglement measure? It'll be 0 on a separable state. I mean, if mutual information is 0. Oh, separable, yeah. So you could take just like a classical Boltzmann density matrix, which is just diagonal on the z basis, and it will still have non-zero entanglement of purification. So an interesting question then, I think some of the early works addressed computing entanglement of purification just with, say, a qubit or 2. But for our purposes, we want to know, if we want to study the behavior of this lower bound, what is the entanglement of purification in many body systems and field theories? So I don't think this problem had been addressed before. And one of the difficulties is, unlike Renyi and von Neumann entropies, where we have a very easy way to represent these computation in terms of path integrals. There's a, just like we were hearing about, you can replicate the system and then study the behavior of twist operators. So we have a nice geometric interpretation of what the Renyi or von Neumann entropy means. Entanglement of purification is expressed as an optimization problem. And it's an optimization problem over an exponentially large space, the set of all purifications, exponentially large in the size of the system. So theoretically, I don't think there's any, we don't have any path integral interpretation of this. And in general, numerically, it's going to be intractable. It's even hard for a couple of qubits because it becomes very rapidly a large variational problem, optimization problem. So let me first just discuss an attempt, our attempt to just try computing it numerically before I'll discuss theoretical calculation of it. So the idea here is, so we'll be working with 1D matrix product states. I can view the problem of finding this optimal purification as one where you start with a Thermofield double purification and then act with a unitary only on the ancilla to try and remove as much entanglement as possible. So that unitary is this U disentangler unitary. So roughly speaking, the way the algorithm works is I'm going to start at infinite temperature, and then at each time step, I do a little bit of imaginary time evolution to cool it down, acting on the physical degree of freedom. So that's the gates on the top here. And then I am allowed to act with any unitaries I want on the ancilla, and I treat it as a variational problem where I choose the gates to try and minimize the entanglement for a cut like this, because that's the entanglement which contributes to the entanglement of purification. Okay, so we're going to variationally choose these gates here, and then compress it back to a matrix product state, and then you just keep repeat. So you're cooling down slowly, and as you're cooling it down, you're disentangling the ancilla. So just to be concrete, I'll say how we actually do this practically. The main problem is how do you choose these disentangling gates acting on the ancilla? So we use the most naive, greedy algorithm you could think of. At each step, we focus on a given bond, and then it's a variational problem over a two-site unitary, and you simply choose this two-site unitary to minimize the entanglement across that cut there. And you just do it in one sweep, going from the left acting on odd bonds, and then from the right acting on even bonds. It doesn't actually matter too much how exactly you do the trotterization. It's a nonlinear optimization problem, and there's not some closed form solution to it, but there's a iterative procedure that I actually first learned about from a paper of Giffrey's. A similar problem shows up in MERA, actually, how to just find gates to remove entanglement. And it's pretty fast. So because it's nonlinear, you'll see, I think this problem actually, if you said, okay, your fitness function is entanglement across the bond, it's some nonlinear function. It actually has many local minima. So the resulting algorithm ends up looking a little bit noisy, but I'll show you it seems eventually to give nice behavior. Okay, so let me show you the result for doing a critical theory. So I'll, of course, do the transverse field Ising model in one dimension at the critical point. And what I'm going to plot here is I have a finite segment of chain. It might be, say, 100 sites long. And I'm going to compute the purification once just doing the Thermofield double state. That's going to be the red curve. And then the blue curve is, rather than doing Thermofield double, I do this disentangling acting on the ancilla. And then I just compute the entanglement for a cut right in the middle of the chain between the left and right as a function of the inverse temperature. So for the Thermofield double state, of course, the entanglement starts at 0 at infinite temperature and then saturates to some value, which is twice the ground state entropy. If we instead do the disentangling, you see at first the disentangling isn't able to do anything. It's the same as the Thermofield double. But then when the temperature becomes of order 1 in units of the coupling constant, the disentangling starts kicking in. And by the very end, the entanglement of the purification is found to be exactly a half that of the Thermofield double. So that's what we expected in this limit. The optimal entanglement of purification, or the entanglement of purification in that limit, should be the ground state entropy, which is half that of the Thermofield double. Okay, so that means by the time we get to 0 temperature, something interesting has happened. We've, we continuously were acting with this disentangler. So on the ancilla, we eventually built up just this unitary network here. And by definition, it needed to have the property that when applied to the ground state, it produced a disentangled state. So it's doing something a little bit similar to the MERA, where it's taking the ground state of a CFT to an unentangled state. But you did it sort of in this gradual process as it was cooling down. Okay, so we'll call this quantity in blue. It's a guess for the entanglement of purification. So we know we're getting the right answer at 0 temperature. There's basically no other way to check, as far as I know, whether this is the actual optimized entanglement of purification, because there's not really any way to compute it otherwise. But it's interesting now to try and check whether this curve, the blue one, has the properties we might expect of the entanglement of purification. So the first interesting thing to check is whether it behaves like a nice local quantity would. It's phrased as a global optimization problem, but does it behave like other entanglement measures where the locality of the field theory is built in? So let's just do a test here. What I'm going to do is take transverse field Ising model on a chain of length L, where L is going to go up to 100. And then I'll measure this sort of guess for the entanglement of purification for a cut at segment of width LA as a function of the temperature, inverse temperature beta. Okay. So what I'm going to plot here is the exponential of the entanglement, and then I'm going to normalize it by the entanglement entropy at 0 temperature. Okay, so then I plot that as a function of beta over L, because I like to see if I can get a scaling collapse. And what you see is for two different sizes of the subsystem, 1/4 and 1/2, across a bunch of different system sizes, you get within kind of the noise of this algorithm a nice collapse. So the fact that it goes to 1 at the end is just telling you that's the limit in which the entanglement of purification should be the ground state entropy. So it's eventually approaching the true entanglement of purification. Okay, so what this tells us, the fact that you get a collapse versus system size here, is that the entanglement of purification is actually, or the exponential of the entanglement of purification is behaving like a scaling operator, and it's a scaling operator with the same dimensions as the von Neumann entropy would be, which is C over 6. So even though it's not obvious from the definition, this entanglement purification is behaving like a nice local quantity. So what is this disentangler, this network we're building up gradually doing? So my original cartoon of it was based on the MERA representation of the Thermofield double state. So we know MERA is a particular, called a holographic network, which can represent the ground state of a CFT. If you're going to represent this Thermofield double state, effectively what you do is you take 2 copies of MERA, you truncate it at a scale set by the inverse temperature, and then you just glue them together. So this is the Thermofield double representation. What should the optimized purification look like? Well, roughly speaking, what you're doing is we're allowing ourselves to act with any unitary on the ancilla. The MERA network itself is a unitary. Well, at least it's an isometry. So it means a just as valid purification here would be to just throw away all the tensors corresponding to the ancilla and just get the MERA truncated at some point. Okay, so what that's going to mean is that the entanglement, which comes through a cut like this and is crossing these red bonds, by throwing away half the system there, you're throwing away half the bonds you cross and therefore reducing the entanglement. This certainly explains what happens once you go all the way to t equals 0. Okay, so roughly speaking, what the optimized purification is doing is peeling off the part of the geometry that isn't causally connected to the physical degrees of freedom. Yeah, so I mean this, yeah, that's right. So this cartoon can only be right as you approach 0 temperature. Okay, so talking with Brian, this led us to start thinking about how to generalize that cartoon, which, as we know, can't be exactly right, into a holographic prescription for what the entanglement of purification should be. So the setting I'm going to look at here is, rather than considering a finite temperature state, let me instead consider a zero temperature CFT on a ring, and I'll partition that ring into 4 regions A, B, C, and D. And then I can look at the reduced density matrix on 2 disconnected parts A and B. Okay, so by definition, the original ground state of the CFT is a valid purification for rho AB, but there's no reason to think it's going to be the optimal one. So what would the picture be for the optimal purification in this case, and hence the entanglement of purification? Okay, so the cartoon picture is as follows, just dealing with it in terms of MERA pictures. If you wanted to write down a tensor network or MERA ansatz for the ground state of a CFT on a ring, you'd take the MERA and put it on a disk like this. And then we notice here that I'm going to partition this network into 3 parts. I look at D and C, which are the parts I'm tracing out, and there's a so-called entanglement wedge here, which are the set of all tensors which only affect the state on D, and likewise that only affect the state on C. Now, if you look at this network here, it has, one of these wedges. It has 2 boundaries, the actual physical degrees of freedom here, and then the bonds you cut in the center. And this set of tensors actually acts as an isometry from the boundary to the interior spins here. And at least in MERA, we can think of that as a disentangling isometry. So if I simply cut out these 2 regions here, I get another tensor network that lives on A, B, and then these 2 boundaries here. And by definition, the actual ground state of the CFT you get by applying these isometries to D prime and C prime. But the key thing is the fact that these D's act as invertible isometries means that AB, C prime, D prime is just as good a purification for AB as the original ground state was. So intuitively, we now expect that this thing, where you just cut out these 2 wedges, is going to be the optimal purification in this case. So the resulting entanglement of purification, following the Ryu-Takeyanagi formula, is going to be the area now cut through this, which separates it in A and B, having cut out those 2 wedges there. Okay, so this prescription actually got scooped by Tadashi about a month before. Leads to a formalization of the holographic prescription for the entanglement of purification. So to generalize this picture here, to compute the entanglement of purification between A and B, first find the RT surface which separates AB from the rest of the system. So that was the red lines. And then you can think of sort of just cutting those out. And then you look for the minimal surface which is able to separate A from B. And because we've separated out those wedges, the minimal surface X is now allowed to terminate either on the Ryu-Takeyanagi surface or just on the boundary itself. So it's the minimal curve separating from A and B, which is allowed to terminate on the RT surface. And then the entanglement of purification becomes the area of that green curve there. So I think what I'll focus on is actually comparing this prescription with the numerics, since it's sort of, we don't literally expect it to apply. This is a central charge 1/2 system, but let's just look at them next to each other. So one thing you'd see is from this holographic prescription, it would indeed obey a scaling collapse with the same dimension of C/6 that we found. Another thing that roughly qualitatively fits is that this entanglement of purification is actually not monotonic. In general, it peaks at some intermediate temperature and then reduces. And generically, that's something you also see in the holographic prescription. Usually there's some peak at intermediate temperature before it goes down to 1. Now in the holographic prescription, there's of course going to be sharp transitions where various RT surfaces switch. That leads, for instance, to the peak before it drops down to 1. We wouldn't really expect to see such sharp behavior here, but at least you roughly see that there's always a crossover scale of order 1 where it peaks and then saturates. I don't have any slides on it, actually. Oh, you mean how this was actually done in this case? Yeah, so this is oh yeah, sorry. So this is, we're plotting the exact same thing. So first, we have to extend the holographic prescription a little bit. The numerics we do on a finite chain rather than a disk. So the first thing is expanding the dictionary to include the effect of the boundary. So this again is using Tadashi's holographic boundary conformal field theory. So then the data we're showing here is so the result actually depends on the boundary condition. So if we use the boundary condition which applies to the numerics, you can then compute the minimal surface from the prescription. And then we're plotting, this is beta over L, where L is the length of the chain, just like this here. And then this is just the holographic result for what the entanglement of purification is as a function of inverse temperature, depending on whether you cut 1/4 of the chain out or 1/2 of the chain out. It's somewhat special here that if you cut half the chain with this particular boundary condition, it is monotonic, but in general it's not monotonic. The next thing I want to discuss is, so far we've been talking about finite temperature equilibrium states, but another system we'd like to be able to address is doing non-equilibrium dynamics. So a typical setup we might look at is operator spreading. So let's start actually, we're going to work at infinite temperature, so we start with the infinite temperature Thermofield double state. Then we act with a spin flip in the middle of the chain, and then do real-time evolution rather than imaginary time evolution on the physical degree of freedom. So this would be the purification approach to watching an operator spread. So we can do an analogous thing as at imaginary time, which is as we're doing the real-time evolution on the physical state, we can try and disentangle on the ancilla. So let me show you the result of this experiment for the transverse field Ising model. There's a bunch of curves here, but I actually want you to focus just on 2 of them. So this here is the time after you act with operator, the spin flip, and the axis here is the entanglement when you cut the purification in half. And let's look at 2 cases. One is when you don't do anything to the ancilla, and then you see this rapid linear growth in entanglement. And then the purple curve here is if you instead do the disentangling acting on the ancilla. And it grows with a much slower slope than the non-optimized one. So we were very excited when we saw this, because naively it means if you thought that the difficulty is basically set by the amount of entanglement, you could go out to times about 4 times larger than before the entanglement was comparable to the not disentangled one. So this would let you do real-time evolution or try and measure Lyapunov exponents and things out to much larger times than before. But let me close by saying one more plot of this is not just showing particular cut, but actually what our version of entanglement of purification is in the plane both of where you make the cut and time here. So this model is actually transverse field Ising model in the presence of disorder, which can lead to many body localization transition. So the color is the entanglement of purification for a particular location of the cut and time. And you see here that the entanglement of purification also seems to obey a sort of light cone. And the spread of the light cone depends on, this is the case where it's clean, and then as you add more and more disorder, the growth slows down, and eventually here it's actually sublinear spreading. Yeah. Okay, so let me just say the problem we're still dealing with is whether this is actually useful for doing dynamics is the following. So doing this optimization certainly reduces the entanglement drastically. But really the difficulty of the matrix product state calculations is the bond dimension itself. So there's another way we could try and measure how well we're doing here, which is to say, let me fix the accuracy with which I want to represent the state. Say I want a fidelity of 99%. What's the bond dimension I need to use in order to keep a fidelity of 99%? So that's how I'm going to instead plot the data here. This is again time, and this is what dimension do the tensors have to be to keep that fixed high fidelity. The red one is the kind of naive no disentangling, and the purple one is doing the disentangling. And what you see is that even though you've reduced the entanglement drastically, naively you might think you'd need exponentially less bond dimension, the required bond dimension for fixed fidelity actually goes up. And what's happening here is that if you look at the entanglement spectrum of the purification, that's what I'm plotting here. So this is the log of the Schmidt values of the entanglement spectrum versus, so this is like the most important one here, and then this is the less important Schmidt states here. And you find that rather than decaying rather rapidly, the entanglement spectrum develops a fat tail. So even though entanglement is reduced, this fat tail is not very amenable to now truncating based on bond dimension. So we find this seems to depend a lot on the model, whether you get this fat tail or not. So the open question I'd be very interested if anyone here has any insight to is this just an artifact of the way we're deciding to remove entanglement? We do it in a very greedy way where we just bond by bond remove as much entanglement as we can. Maybe there's a better prescription for entangling where not only do you reduce the entanglement, you actually don't introduce these fat tails. Or could it be that this is like real physics, that the true entanglement of purification and the true optimized purification, when you're doing these non-equilibrium quenches, may actually have fat tails in the entanglement spectrum. So we'll need new theoretical tools, I think, to be able to see which of these two possibilities is occurring. So with that, thanks.
Okay, thank you, Mike. So we have time for questions.
And this holographic prescription that you have in this slide,
yeah,
was even there. I guess it's obvious that it satisfies one of the bounds, right?
Yeah. So we show in the I didn't include the slides here, but we show in the paper how so for instance, the inequality that it's greater than mutual information over 2 will all follow geometrically from this prescription. We can do it on the blackboard after.
Okay.
So in holographic, we often have a phase transition behavior.
Yeah. So you get
and
these,
do you see some analogous transition in your numerical computations?
I mean, not
of
really.
Of course, this is a free, I mean, not exactly strongly coupled theory, so we don't expect complete matching, but
yeah.
some analog of this.
I mean, I suppose the analog is just this crossover behavior here, where you get a peak. So basically, up to this point, the disentangling doesn't really do anything up to this point, and then you start removing entanglement and it goes down. So I think this peak is presumably roughly the analog of that kink there, which is the phase transition in the entangling surface.
More questions? Well, I have a question which is related to the way in which you connect the entanglement with the bond dimension.
Yeah.
So actually, we know examples for which the bond dimension can be very small, but the entanglement entropy can be infinite even.
Right.
And you can still approximate it very well.
But is this with a non-uniform?
With a non-uniform.
Yeah.
Right. So it turns out that it seems that the von Neumann entropy may be not the best way of connecting them, but rather alpha Renyi entropies with alpha smaller than 1.
Right.
So could you use?
Yeah. I think that's a great, So I even lied a little bit here. So the actual minimization in this data, for instance, is using the second Renyi entropy. And as you're saying, we probably need a Renyi entropy less than 1. So what we tend to see here is that when you use Renyi entropy of either 1 or greater, it really prefers just what it's doing to the most important Schmidt states and doesn't care too much about the tail. So it may be that using alpha less than 1 improves it. The difficulty is for any alpha less than 1, the minimization problem becomes much more difficult. I think it's tractable, but
and then maybe a related question. So we also know some cases for which you would need an infinite entanglement, but of purification. Whether you use matrix product operator, will have a finite bond dimension.
Right. Yeah.
So maybe you do the simulation, just using matrix product operators and not purifications, then you can gain more than with
Right, right.
doing it.
Right. So, I mean, that won't be true for equilibrium states, but for general, like for equilibrium, the TFD will always be as efficient as the density matrix. But you're saying for a general density matrix, finding the purification, the bond dimension can go away.
For example.
Yeah, yeah. The question is, I'm not quite sure how to. It'll be hard to figure out how to try and test that, because doing the density matrix computations are difficult because you lose positivity and so on. So it will be.
But this doesn't matter so much, because at the end you want to have to predict observables, and
yeah.
you may have a density operator which is maybe a negative eigenvalue, but it doesn't care about predicting observables. So you
right.
measure distances, like one norm distances and things like that. You can work with matrix product operators and have a more
right.
efficient description.
Right. Right.
Okay. Any other question? Well, if this is not the case, let's close the session and thank all the speakers.